So, what I'd like to introduce you today is something called the 3N+1 problem. I'm calling to that. It's also called the Collatz Conjecture. Okay. I believe that's spelled like this. Collatz Conjecture. Okay. It's unsolved in the way the problem was originally presented. So let me explain to you what the problem is. We're going to create a sequence of numbers by doing the following. Okay. So little notation here. When you see a sub n, that means the term of the sequence, the nth term of the sequence, is equal to the following. You take the previous term, which you denote as a sub n minus 1. So this might be if n is 5, this means a5, the fifth term of the sequence, is going to be the fourth term of the sequence multiplied by 3, then you add 1, if, I'm sorry, hold on a second, if a sub n minus 1 is odd. Okay, so if you have an odd number in a sequence, you're going to multiply that number by 3 and add 1 to it. Now, what else could happen? It could be the case that that term is even. So if it's even, we divide it by 2. Okay? And the way to start off one of these sequences is to pick a number to start with and then just apply the rule and see what happens. So let's start with, we'll pick a starting number of maybe 11. We'll start with 11. Okay? So you take 11, and it's kind of interesting when we talk about this now. It kind of looks like a piecewise function, doesn't it? Right? We just finished talking about piecewise functions. So 11 falls into which category? Well, it falls into the first category. It's odd. So to get the next term in the list, we're going to take that number, that odd number of 11, we're going to multiply it by 3 and add 1. So that's be 33 plus 1, or 34. Okay, then. So now, we're going to continue this game for a while. And we may not be sure what's going to happen. But 34 is even. And according to this rule, we're going to divide it by 2. Because if the term is even, we divide it by 2. If we divide that by 2, we get 17. Yeah, correct. All right. 17 is odd. So we'll do 3 times 17 plus 1 is 52. 52 is even. So we'll divide it by 2. 52 divided by 22 is, by 2 is 26. 26 is also even, so we'll divide that by 2. We'll get 13. 13 is odd, so we'll multiply it by 3. We'll get 39. We'll add 1. We'll get 40. And it sure seems like we're just doing this for no reason, but just patient. You see something interesting happen. 40 is even, so we'll divide that by 2. We'll get 20. 20 is even. We'll divide that by 2. We'll get 10. 10 is even. We'll divide that by 2. We'll get 5. 5 is odd. We'll multiply it by 3. We'll get 15 plus 1 is 16. 16 is even. We'll get 8. 8 is even. We'll get 4. 4 is even. We'll get 2. 2 is even. We get 1. And 1 is odd. 3 times 1 plus 1 is 4. 4 is even. We divide by 2, we get 2. 2 is even. We divide by 2, we get 1. Ah, look at that. And then we get 4 again, because 1 is odd. We multiply by 3 and add 1, and we get 4, 2, 1. 4, 2, 1. Forever. Okay. So the first question is, are we sure that this thing's always going to land on 4, 2, 1? So you need some kind of proof for that, some kind of good reason to say, yes, this thing would always land on 4, 2, 1. And the question that Collatz had presented, the Collatz conjecture, was that could we come up with a way of predicting how long it would take to get from our starting term to the first one in the sequence? So if we believe every time that we start with a number we're going to land on 4, 2, 1, then the question is, how long does it take, if I even know what number I'm starting with, to get to a 1? Now, we could actually write it out like we did here. We could count that up. So the number of steps it took, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? So we're going to make a little chart here. I'm going to say starting number. And let's just be careful here. Starting number is going to be 11. And I should note also we went from 5 all the way down to 16 there, so I skipped a step. So that means the number of terms would have been 15. Okay. All right. So let's start with a different number and see how things go. Okay. So I'm going to pick two numbers that are right next to each other. Ready? Let's pick 32. And that one happens pretty quickly, right? 32 is going to even, so it's 16. Even, 8. Even. Oh, and there's the 1. Right away. That didn't take very long at all. So 1, 2, 3, 4, 5 steps. So we start with 32. It takes 5 steps. And just for fun, try 31. So if you try to do 31, the results look like this. Starts off just fine. And then you start to notice the numbers just keep coming and coming and coming. And a sort of interesting question would be, how high does this sequence get? What's the highest number you get? I think we got something in the 9,000s right here. That's the highest number. We never went over into the 10,000 range. So 9,232 is the largest number we get as we proceed through this. And then when everything's said and done, right at the very end there we get 421, 421, forever and ever and ever. Okay. So now let's go back and remember what the point of this was. We're trying to figure out, is there a way, if we know these numbers as inputs, then we'd be able to do something to it, maybe like square it or add it to itself 3 times and multiply it by 7 or some formula like that. And the answer I got back from the formula would tell me the number of terms it takes until I land on the first one. The first one as in 421, 421, and so forth. You could see how complicated this would be because this formula has some pretty strange stuff. For a number like 11, it only takes 15 terms, but by the time I got to an input of 31, I need 108 to be returned from my function. And then with 32, I'd get back down to 5. Okay? So there are certain kinds of numbers you could look at right away and say, oh, this isn't so bad. You know, maybe something like 64 or 32 or 16, maybe 128. All those numbers are powers of 2. So they're always even when you start dividing. Like, for example, 16, 8, 4, 2, 1. 32, you divide that once, you get 16, and then you're in this list. 64, you divide by 2, you get 32, and then you're in that list. 128, you divide by 2, you get 64, and then you're in this list. So powers of 2 are easy to handle. You could predict how long the sequence would be in that case. But other numbers don't seem to do as well.